In a stream of speech of any language, you can expect that there are some sounds that are more likely to follow one than another. The reason for this is that within a given language there are certainly some rules that restrict whether sounds can be at the beginning or the end of a word, but there are only a fixed number of words within any given language. So consider for a second the word limit. If I were to repeat for you just the first syllable, lim, then the likelihood that the next syllable would be it is much higher than that it would be an or ud or f or uck or ap or anything else. Because even though all of those other alternatives are possible words in English, like liman or limud or limf or limuck or limor, all of those are possible sounds, but they aren't words that appear in English. So given that I just said lim, the likelihood that I'm going to finish that word with it is very high compared to any of those other possible sounds. Now, the remarkable thing about sharing this principle is that infants are capable of calculating and tracking the probability with which they have heard in the past one syllable followed by another syllable. And in some subconscious way, we're not really sure how it happens, but infants are capable of comparing how often they've heard those two syllables in connection with each other, compared with how often they've heard that syllable, regardless of whether it was followed by one sound or another, or any sound at all. Now, this ability, called the calculation of transitional probabilities, is reflected in the formula that's on page 117. Now what this formula is demonstrating for us is, at the bottom of the equation, we've got the frequency of x. That would be the frequency of hearing any given syllable, like lim. Now we could hear the syllable lim at the beginning of the word limit, or limber, or limp, or limerick, but we could also hear in the middle of words like acclimate, preliminary, or at the end of a word like slim. And given all those possible situations in which an infant might hear the syllable lim, he or she will calculate the probability specifically as the numerator of that equation that he would hear it as the next syllable. The reason we know babies can do this is because we've created artificial languages and we present them to infants for several minutes at a time. And these artificial languages contain sequences of syllables that could be parsed in any number of ways, but they appear in repetitive manners, so that there's actually only a few possible words that have been repeated over and over again. And we want to see how likely it is that infants can pick up on the fact that those syllables are going to occur in close proximity to each other in that exact sequence in the future. So we present to them, during a test phase, some of the words that they heard in the artificial language, and some misrepresented words that were the same syllables used in the artificial language, but just mixed up. And we see if infants spend a different amount of time looking at speakers that present the two different types of words. And since they can make that distinction, then we conclude that even though this is counterintuitive, infants are actually calculating the mathematical probability that given one syllable, another syllable is going to follow it. Now, I don't know whether this next fact will make it more or less believable that this is possible, but it's not only infants, but animals too that have the capacity for calculating these transitional probabilities. For instance, some research was done with tamarins and showed that tamarins were able to perform as well as infants on this task. And then, when researchers wondered whether this was maybe like an evolved trait in primates, they did it again with rats and found that rats were able to do as well as infants. And not only could infants of 8 months old do this, as well as animals, but also infants of 2 days old had brainwaves that responded differently to those syllables that were more likely to follow one syllable in an artificial language than another. Now, in the digging deeper portion of our chapter, we learn a little bit more about the calculation of these transitional probabilities. For instance, we learned that not only can infants calculate them forward, but they can also calculate them backward. in order to learn something about like the part of speech that a given word is. For instance, if you were to hear a word like bottle, then that word is more likely to be preceded by the word or the than another word, indicating that that word is a noun. And by calculating that backward probability, infants can infer what part of speech given words are. We also found that there are certain kinds of probabilities that are more likely to be calculated than others. Those that are more naturalistic, that are more likely to occur in real-life settings, are more likely to be calculated by infants. But there are artificial languages that researchers have invented that follow arbitrary rules that are unlikely to appear in real life, that infants don't calculate the probabilities. Even though the probabilities are there and could be calculated, the infants don't pick up on those, suggesting either that this is a nativist kind of structure that allows infants to calculate the probabilities based on an evolved cognitive capacity for calculating them, or, and given an anti-nativist perspective, that languages adapt themselves to the cognitive structures that we are born with. Still, it's important to note that despite the fact that animals have this ability to calculate transitional probabilities, that they don't do it in the same way that human infants do. There's a paragraph right at the top of the page of 121 that suggests to us, though the authors don't describe in what way, that animals are calculating transitional probabilities in a less sensitive manner than human infants are.